Delaware Tech, Chem 100, Chem 110, Unit 2 continued, states of matter. While there are many states of matter that are known, the three most prominent ones on planet Earth are solids, liquids, and gases. And these are easily distinguished from one another, not just by their molecular properties, but by the shape that's visible of these three states, the volumes they occupy, how compressible they are under high pressure conditions, and the effect of temperature in terms of expanding or contracting. Let's look at solids first. As you can see in the diagram here, solids tend to be very compact. The dots represent atoms or molecules, depending on the substance, and in a solid they're very compact, sometimes even in very ordered crystalline forms, but not necessarily. But there's very little space between these individual particles. Whereas in liquids, we start to see more space and the particles can move around a little bit. And in a gas, the particles are completely separated. They're not linked to one another, and they're not bonded to one another even a little bit. They're actually just bouncing around at high speeds within the container. If they hit against one another, they do not adhere to one another. So what does that mean? Well, when we have a solid, it will have a definite shape. It'll have a specific shape. If you look at a desk, and I move the desk from one part of a room to another, it still has the shape of a desk. The volume of the desk doesn't change as I move the desk around the room. It's solid, and the volume is very specific. It's very definite. It stays the same. Is it compressible? Well, yes, if we put it under enormous pressures, it would be compressible, but under normal high pressure conditions, solids do not compress by very much. And related to the compressibility is the effect of temperature. If I warm up the solid, it might expand a little bit, but not very noticeably. So we're going to say that it's not compressible and that the effects of temperature increase are very minimal, so it's not affected by that either. If we look at liquids, liquids don't have a definite shape. You know that if you had a bottle of water and you poured it on the floor, the shape of that water would take on a completely different shape. However, the volume of the water in the container, in the bottle, would be exactly the same volume as if it was sitting on the floor. It would just have a completely different shape. Now, is a liquid compressible, and does it expand that much when you increase the temperature? Well, just like solids, no. You really have to put it under enormous pressures to change its volume, and you really have to warm it to great high temperatures in order to expand it. In fact, it really will not expand appreciably until you turn it into a gas. So again, the shape will vary. It'll be dependent on the container it is in or sitting on in this case. It has a definite volume, so that doesn't change. It's not very compressible, and there's very little expansion when you warm it up. Gases, on the other hand, they do not have a definite shape. They'll assume the shape of the container. If I had a container of compressed gas in an empty room, in a room under a vacuum, that gas at that moment is occupying the shape of the tank that it's in. However, if I open it up, the gas will fill up the entire room and will occupy the shape of the room. So a gas doesn't have any definite shape as well, just like a liquid, but it doesn't have a definite volume either. A gas will occupy whatever volume you give it. It will expand or contract to fit that volume. And this leads to the next answer. Is it compressible? Yes, it's highly compressible. And in fact, when you warm up gas, gas will expand tremendously. So there are great differences between solids, liquids, and gases. The big difference between solids versus liquids and gases is the shape. Only solids have a definite shape. Whereas if we look at the volume, whether it's a definite volume or not, only gases will have a variable volume. The other two will have a very definite volume. And only gases really are affected tremendously by pressure or temperature in terms of their volume. So let's look at these three states of matter: solids, liquids, and gases. And these can all be converted to one another relatively easily with changes in temperature or changes in pressure. And we actually have words to name every one of these transitions of changing from one state to the other. If we look at solids going to liquids or liquids going to solids, there are words for these processes. In fact, solids going to liquids, you probably already know the common name for that. That would be melting, though chemists have a very specific name for that called fusion. Unfortunately, the word fusion has another meaning in chemistry as well. When we're talking about nuclear chemistry, fusion refers to fusing the nuclei, the centers of two atoms. But in this case, we're just going to use melting or fusion to mean the transition from solid to liquid. Liquid to solid, I think you all already know. If you think of these in terms of how we use the words to describe water, well, that would be freezing. And it's used for other substances as well. So melting and freezing are the opposite processes of solids going to liquids and liquids going to solids. We also have liquids and gas transitions, and liquid to gas has several words for it. We call it boiling, we call it evaporation, more properly we call it vaporization. So you might hear about the heat of vaporization in chemistry. And going from gas to liquid, you've heard this word, it's not as common, but we say condensation. Condensation is when you're going from a gas to a liquid. Think about condensation on the outside of a glass of ice water. The outside of the glass, you'll start to see droplets of water. Well, those droplets come from the water vapor that happens to be sitting in the air around the glass. And when you put this cold glass in this room, well, the cold glass will cause some of the water vapor in the air to condense and become liquid on the outside of the glass. We also have two more transitions, and these are definitely not processes people usually think about: solids going directly to gases or gases going directly to solids. And the word for solids going directly to gas is sublimation. You may have seen chunks of dry ice turn into vapor, to white clouds of vapor, especially at Halloween time. People love to do this. Well, that process of going from a solid to a gas directly is called sublimation. It is sublimating. The CO2, the dry ice, is sublimating back to carbon dioxide gas. Well, the opposite process of going directly from gas to solid is called deposition. You might find this in high-tech processes where you take some metal, turn it into a gas first, so you heat it up under tremendous temperatures, frequently using electricity, and the gas is the metal vapor is then allowed to cool on the surface of some object. So this is one way that people plate precious metals onto other substances by letting, say, gaseous gold or gaseous silver deposit as solid silver or solid gold on the surface of some cheaper piece of jewelry. So, just to review, solids have a definite shape and volume. It cannot flow unless you grind it up into little tiny particles. But we're talking about actual physical-looking solids. Liquids have a definite volume, and they take the shape of the container, and they do flow. Gases don't have a definite shape or a definite volume, and they can definitely flow as well. We don't always think of gases as flowing, but both liquids and gases are considered fluid because they can flow. In addition to these three states of matter, we have other ways of thinking about them. Vapor is another way to say gas, but we tend to use the word vapor when we're talking about gas that's formed below the boiling point of a specific substance. In other words, water vapor. You can have water vapor even at room temperature. If I had a glass of water sitting on a table, that glass of water is always producing a little bit of vapor that goes into the air. Of course, most of the water stays as liquid in the glass, but there's a little bit that has vaporized, that has evaporated. So we tend to use the word vapor when we're talking about below the boiling point, but this is not a hard and fast rule at all. People also use the term vapor to mean high temperatures as well. In addition, we have these two other states of matter that aren't as important in this class, but they are important in the rest of the world. Plasma is hot ionized gas. So if you warm up a solid, it will typically turn into a liquid. A liquid will frequently turn into a gas or vapor when you warm it up. And if you heat up gases high enough, the particles that make up the gas will start to break apart, and you'll form positively charged ions and negatively charged ions. And in fact, this hot ionized gas is what all stars are made of. In fact, plasma is probably the most common form of matter in the visible universe. Then we have some more exotic forms of matter, the Bose-Einstein condensate. And the Bose-Einstein condensate was named for a scientist from India by the name of Bose, and of course, Albert Einstein. This actually came about because Bose had this brilliant idea. He knew that people weren't going to listen to him, so he wrote a letter directly to Einstein, and Einstein agreed it was a brilliant idea. And they realized that there might be a form of matter if you cool atoms down to extremely low temperatures, down to what we call absolute zero, the lowest temperature possible. And that under these conditions, certain types of atoms will actually cluster together and behave as if they're a single atom. And now you don't need to know this for the course, but I thought it'd be interesting to talk about. So let's talk about phase diagrams, and these look very foreign to people who have not seen them before, but this is a diagram that shows you when a solid, liquid, or gas would be present in a substance depending on the pressure or the temperature of that substance. So on the y-axis, you see that's labeled in terms of pressure. Low pressure at the bottom of the graph, high pressure at the top. And on the x-axis, we have temperature, and this is in degrees Kelvin, which goes down to 0. So 0 is the lowest temperature possible, called absolute zero. And it goes up to, in this case, about 300. Kelvin can go much, much higher, probably over 1 trillion degrees as far as what is possible. But this is up to 300. This is a little bit warmer than room temperature, believe it or not, 300 degrees Kelvin. So this chart goes from cool to warm on the x-axis, and it goes from low pressure to high pressure on the y-axis. So you'll notice the chart is divided into 3 very specific regions, and there's a little box in each of those for labeling those 3 regions. So if we look at the box that is located on the left here, this box, I'm sorry, I'm labeling these a little early. If we're looking at these boxes and we see this box here, this is an area that is in low temperature and higher pressure. In other words, it's the pressure that's it's part of the graph that's in the higher pressure range and the lower temperature range. And that's what you'd expect for a solid. Solids are made when you cool things down, but solids can also be made when you press the particles together tight enough that they become more solid. So that makes sense. Let's look at gases now. Gases are in the region that is in higher temperatures and the lower pressures. And that makes sense too. How do we get gases from, say, water? Well, we warm up the water high enough to a high enough temperature, it will become gaseous. It will become vapor. We can also make liquids or solids turn into gases by lowering the pressure so much that it forces these particles to evaporate and become gases. And then under certain pressure conditions, you'll notice below this pressure, you can never get liquids. But above this pressure, liquids are possible between the solid and the gas. And that makes sense. If you're warming up, let's say we're existing at this pressure, and as you warm up the solid, it turns into liquid first, and if you warm it up high enough, it will turn into gas eventually. Whereas if you're doing it at low pressure for this particular substance, low pressure, you're working down here at this pressure, you'll notice it goes directly from a solid to a gas and skipping the liquid phase. Now, this is a phase diagram for a made-up substance, so every substance has a different shape to this phase diagram. But you can imagine water at 1 atmosphere pressure, normal pressure, goes through these three phases. It goes from solid to liquid to gas at normal pressure when we warm it up. Whereas carbon dioxide behaves differently. Carbon dioxide only goes from solid directly to gas. There is no liquid phase unless we increase the pressure, then we can find a liquid phase. So I'm going to clear these notes because they get a little confusing here. So those are the three phases and how to find them. Liquid will always be this one that's in between the solid and the gas. So let's look at a transition. Here's a typical transition. It starts in pressure of 20 atmospheres. So 20 atmospheres would be somewhere around here. You'll notice this scale is not what we call linear scale. It's a log scale. It changes pretty abruptly. We go from 1 to 5 to 73 here. It's obviously not evenly spaced, but that's because we need to squeeze all the information onto one chart, and this is one way to do it. So we'll get rid of that and that. So we're up at a certain pressure here, and the temperature we're starting at is 197 degrees Kelvin, which would correspond to roughly this temperature here and this pressure, which puts us at this spot right here. So we're starting at this point. We're clearly at a solid phase of this particular substance, but we're going to warm it to 230 degrees Kelvin. Well, 230 would be somewhere around here, so we have to move this over here, and you'll notice now this substance has become a liquid. And I'm going to erase this and show you this on the actual slide. So this is a transition from solid to liquid, so this would be a melting or a fusion process. We can also look at a transition that's moving from one pressure to another. So let's say we started at 200 degrees Kelvin, so roughly the same pressure that we're at, temperature that we were at before, and we're going to start from 0.5 atmospheres of pressure. So this is half the pressure of our normal atmosphere. So that would put us at about this point here, about half an atmosphere of pressure, and at 200 degrees Kelvin. And now we are increasing the pressure. So we're increasing the pressure. It's going up to 5.2 atmospheres of pressure. And you can see we used to be at a gas phase, and now we have gone to a solid phase. So this is an example of deposition. Remember, going directly from a gas to a solid, you're depositing the gas as a solid on some new object or surface. That's a deposition. Now, the triple point is something we haven't talked about. The triple point is a position which is defined as the temperature and pressure where all three states are possible. Now, something I didn't directly state before, but if you looked at, say, the lines between these different phases, this line right here, if you're anywhere on that line, you're in a place that can have both the solid and the liquid present. If you're over here, you're in a place that can have both the liquid and gas present. In other words, this pressure and temperature right here, this pressure and this temperature, corresponds to a state that can have both liquid and gas present. In fact, that would be the boiling point for that particular pressure. Whereas points over here on this part of the line represent temperatures and pressures where both solid and gas can coexist. So what that means is that there is one point where all three can exist, and that would be what we call the triple point. And the triple point, that's pretty easy to remember. It's the point when all three states of normal matter, solid, liquid, and gas, can exist at the same time. And in this particular case, the triple point is defined as 5.2 atmospheres and 216.6 degrees Kelvin. We also have another point on this chart called the critical point. The critical point is the temperature and pressure at which point we can no longer distinguish between liquid and gas. Well, look over here. This is the transition between liquid and gas. Any one of these points along this curve, you will have both liquid and gas. However, once you get to too high a temperature and too high a pressure, you can't tell anymore. So above that point E, we have no idea where the division of gas and liquid is, and we refer to this as the critical point because liquid and gas, the liquid has become so high a temperature and so high a pressure, and the gas has become so high a pressure and so high a temperature that they really meld into one another. They become indistinguishable from another. In other words, the gas is thinner than you'd expect. The liquid is thick. The gas is thicker than you expect. The liquid is thinner than you expect, and they really become one confusing state that blends the two. So we really can't even tell what it is above that point E. That's called the critical point. And the critical temperature and the critical pressure would be the ones corresponding to that point. So let's look at a phase diagram. See if you can find where the solid, liquids, and gases are. Now, you'll notice the transition here between point C and point D. That line, sometimes that line is straight up and down, sometimes it leans to the left, sometimes it leans to the right. It's different for each substance. But in any case, you will always find solids on the left and upper, and the gases on the right and lower, and the liquids will be in between that. So that tells us that the solids are A, the liquids are F, and the gas phase would be represented by the area where E is at. Let's talk about some transitions. Melting and freezing. So melting and freezing are the opposite of one another. Melting is going from a solid to a liquid. Freezing is going from a liquid to a solid. So we merely look for the solid phase area and the liquid phase area, and anything along that line between D and C and continuing on up, that's the transition of melting or freezing, depending on which direction we're going. Boiling and condensing, that would be going between liquids and gases, so that's between the area where F is at and the area where E is at. So anything on that line between D, G, and H would represent the transition of boiling to, the transition from liquid to gas or gas to liquid, otherwise known as boiling or condensing. So anywhere going from one side of that line to the other, and G is just one of those many points. And then subliming or depositing, that's going from a solid to a gas or a gas back to a solid. That would be going from the area where A is at to the area where E is at or back. And we find that transition would happen where we have the line that includes point B at. So any part of that line where B is at, that would be subliming or depositing, depending on which direction you go. And of course, the triple point is where they all meet at point D. The critical point is point H, where you no longer can tell the difference between the area F is in and the area E is in. In other words, you can't tell the difference between liquids and liquids and gases. And we'll switch over to the next module after this.